Hi everyone, my name is Kenneth, and I'm here to explain the concept of forward kinematics in ECE 470 Introduction to Robotics. Why do we need forward kinematics? When deriving systems in two dimensions, it may be simple enough not to need the forward kinematics equation and derive them analytically. However, as the complexity of these systems grow in three dimensions, the equations to define the position of the end effector becomes increasingly more complex. Forward kinematics allows us to more compartmentally derive these equations, making it easier to derive the location of the end effector, especially in more complex robotic systems. What is forward kinematics? Forward kinematics is an easy way to get the position of the end effector tool in the world coordinates. Given joint angles and concepts like transformation matrices, the zero position matrix, screw motion, and the product of exponentials, the equations for forward kinematics can be derived. This allows us to obtain the end effector pose in the space frame for a set of given joint angles. To review, the transformation matrix is defined as the rotational and translational displacement between frames. Here, we see R as the rotation matrix and P as the translational displacement. Looking further into the nomenclature, the first number represents the frame that it is being expressed in, and the second number represents the frame that is being expressed. This example represents frame 4 being expressed in frame 0. Furthermore, if there are multiple transformations, the transformations can be compounded, transforming one frame to the next until the end effector. Here, frame 1 is expressed in frame 0, frame 2 in 1, and so on, all multiplied to create the overall transformation matrix from frame 0 to 4. The zero position matrix represents the resting position of the robot when none of the joints are actuated. This is represented as the M matrix, where the matrix is defined as a transformation from the space frame to the body frame of the end effector with no joints actuated. Here, the joint displacements is defined with the zero vector, and the rotational and translational displacements also reflect this as well. Looking at this example, we can see the zero position of the robot on the right, where we define the matrix M. Rotation matrix R and vector P are defined as the rotation and translation required to move from frame 0 to 3. These values are combined to create the matrix M for this system. The screw motion can help us understand how a particular frame would be affected by deviation from the resting position. In many applications, revolute joints are used, which have screw motions but no pitch. For each joint I, the screw motion must be defined with Wi being the axis of rotation in the space frame, Qi the distance to the joint in the space frame, and Vi the linear velocity vector in the space frame. These values can be used to define the screw axis of a specific joint to create the skew symmetric axis of the screw symmetric matrix of the screw axis for a given joint. In this example, we define the screw axis for joint 2. We find W2 and Q2 through the zero position of the robot and take the cross product of the two components to generate V2. The vectors W2 and V2 are combined to create the screw axis for this joint. Once we have the skew symmetric matrix of the screw axis for a given joint, we can use the given joint angle to calculate the transformation based on the joint displacement. This can be done through the product of exponentials and matrix exponentials. By taking the product of the screw axis and the joint angle displacement, the transformation matrix from the joint displacement can be calculated. Looking back at this example, we can use the screw axis generated and the given displacement for joint 2 to calculate the transformation matrix. We use the screw axis of joint 2 to generate the transformation matrix from 2 to 1 if joint 1 is not actuated. Putting all of these components together, we get the following generalized forward kinematics equation for end joints. We can see the compounding transformations at each joint, all multiplied by the zero position matrix to obtain the end effector pose given by a set of joint angles. Going back to our example, we can apply this knowledge of compounding transformations to the zero position matrix, given that we find the screw axis and joint angles for each joint. To summarize, we use forward kinematics to derive the end effector position for a complex robotic system in 3 dimensions and apply them to a 3 revolute joint example in the process. That has been the concept of forward kinematics, and I hope you learned something from this tutorial. Thank you for listening.